Good morning, everyone. This is Rugambwa Gloria. I'm a member of Group 17, and our project is a multimodal machine learning architecture for food supply chain optimization, mitigating the SIM-to-real gap in demand forecasting. First and foremost, this project coverages Makerere University. We are looking forward to solving food wastage, unpredictable demand within our university. So let me take you through. Starting with our introduction and background, we're able to move within this university and we collected a little data from the different food vendors and cafeterias running within the university. And we saw that there is a huge problem of unpredictable demand on certain seasons, within certain seasons in the academic calendar. So we were able to see that the university serves actually a large number of students whose consumption patterns shift time from one time to another. And this actually affects the vendors in such a way that, let's give an example of during the examination period, and a food vendor has stocked his shop or kiosk with food, but he's not well informed that actually the examination period has started. And during such times, the number of customers is less compared to during the normal academic time. Now, this will lead to food wastage and later low revenue in the long run. So this system that we are trying to build, that we have built, looks forward to solving such a problem. In the long run, we are also helping these vendors to get a living out of whatever they sell. And the problem statements, we had a domain one, which was food on some days leading to wastage and revenue stability. That's what we are actually trying to solve. Then the computational problem, here this is one that we encountered as we were working through the project, and this is a SIM-to-real domain shift. Next, we're able to come up with research questions to help us expound and see whether we are on a right track, to also help us question and carry out some data analysis within this project. And these were our objectives, which were to analyze food demand patterns, identify demand-supply mismatches, quantify waste and its financial impact, and others. So our methodology and system architecture, we used two data sets. We had the cafeteria data set, which handled all data from major cafeterias running within the university. These include Guild Canteen. Then we have COSIS Cafeteria, CEDAT Cafeteria, Choose Cafeteria, like basically the main food points within the different departments in the university. So then the kiosk, this was handling the small food outlets, like the shops within the university too. And then we carried out data pre-processing on both the data sets, then used a number of models, from which we later chose the best model that will help us give better prediction and would also handle large amounts of data. So as I'll show you in the next slides, we used 12 different models, but later came up with one model, which is the HDB scan model. Yeah, then, as I had said earlier on, our dataset description, we used two datasets, which were synthesized based on the small data we had retrieved, we had collected, we then had to obtain our own data based on also that researched data. We didn't just generate data from chat or what. We had to collect, then try to get our own data based on what we had collected. Then the models that I had said earlier on, these include the Bayesian network model. Here we are using probability statistics. It's going to help us understand which feature within our data sets has a huge impact on this demand. Then we had the Sarima model, which is to help us capture distinct demand patterns within the various customer groups. We had the long short-term memory. This one is, we used it based on 21 days, like to predict the future. You use the past history to help you predict the future demand. Then we have the XGBoost, which is going to learn from historical cafeteria data, how operational decisions, then sales volume, waste, so that you can determine the profit. HDBScan, which is actually the one we used finally, it helps to automatically detect outlier days. Outlier days, these are days where it's extremely, either there is extremely high demand or there is extremely low demand. Then we had spectral clustering, agglomerative clustering, which is to reveal the structure in temporal demand patterns. Batch clustering, here we are going to see still variations in temporal demand patterns. Autoencoder, which is also to help us identify the abnormal days within the academic period. Then Gaussian mixture model, Prophet model, and isolation forest. This is our model comparison with the different strengths and weaknesses for the different models. HDBScan, it had a moderate computational cost. Spectral, it was good enough. Autoencoder, and so many others. This table here shows the difference in the results obtained. And it's from this table that we are able to come out with which model would actually have a greater effect, would be effective in this demand prediction. And we came out with a HDBScan with a silhouette score of 0.5, which is actually a good one. Davis-Bouldin, and then a Kalinske of Harabas. This Kalinske helps to show the difference, how different are the clusters from each other, and how is the difference in the clusters formed. Yeah. Then the Davis-Bouldin, we had 0.6 accuracy. So going on to our selected model architecture, we used the cafeteria features within our cafeteria dataset. It went through computational mutual reachability distance. Here is where it's going through the cleaning, it's going through the checking of whether they are actually null values, changing of dates to the right format. Then it goes to building of minimum spanning tree. This, you're preparing the data for good clustering so that you can obtain good clusters. Then the next was constructing a cluster hierarchy. Then it went into extracting stable clusters. We were able to get 3 clusters. Then later we assigned noise labels, which are points not meeting the density criteria. Then later were the output of cluster 0, 1, and noise. So our output results for the HDB scan model. You can see there is a scatter plot here showing the different clusters. One is highly congested, another one is scattered, another one is. So the highly congested is the cluster 0, followed by cluster 1, then the noise. And then the bar graph that showing the academic period by clusters, we are able to see that cluster 1, cluster 1 shows that it's the leading cluster during the semester teaching that has the highest demand pattern. Highest demand during semester 1 teaching, then in exam period it reduces, then in semester 2 teaching period it hikens up. Then we had we had a bar plot showing the outlier differences within the clusters, then a box plot and a scatter plot. As I said earlier on, cluster 0, which is the cluster that demonstrates it, represents the low demand, which is the demand that actually occurs on a daily. Consists of standard operational days across the most cafeterias. Then we have cluster 1 with high demand. Here it consists of like the high volume hub, the days where unexpected there is a high number of people. Then we had the noise, which is where we have the extremely low demand days, for example, during class, let's say during weekends, where very few people are within the university, depending, some weekends could actually be having conferences and there are many people, but on certain weekends, then also during the academic examination period. Next, we had our deployment pipeline. We had a GitHub repo for keeping our project on cloud. Then we had a Docker image build. Docker was to help in containerization of the different project structures. And then we had a model artifact, which is HDB scan. Then the Gunicon server for handling the requests, and then a startup health check, and then a service live. We used Render for deploying our model. Why we used Render is because it's cheap and affordable and one can easily deploy their project. So this is how our interface looked like. We had a kitchen and kiosk supply tracker. This is kind of like a dashboard display. It will show the number of suppliers. It will show the items in stock, those running low and those on order. So this interface will be used and interacted with the vendors and the suppliers. This same interface is able to analyze the demand pattern, the recommendation action, and a suggested restocking in case there is need of one. So this is our operational flow of the system. It starts with sending a request. Then the request is received based on the features from the vendor UI. Then they are validated and the feature schema checked. Validated, that means it sees, is this whatever this person has entered, is it available? Is it in stock? Is it out of stock? Then it will standardize them. Then it will predict which cluster this vendor, for all the sales he has made within that period, within that day, which cluster does he fall in? And then the output will show his label and a recommended action. What can he do? What should he restock? How can he handle the next sale? That will all be in the output map. So our HDB scan, we had to use a compression technique too. So we had 3 techniques, being 3 people in our group. First is the coset stroke prototype method. As you can see from the diagram, it gets the original data set, clusters using k-means clustering, then centers these clusters into different it partitions them into centroids. Yeah. Then the HDB scan will then use these centroids to then map the original earlier on clusters to these centroids. So how this is actually helping is that it increases the number of clusters from 2 to 3. Then also it helps to decrease the SOH score, though decreasing it will actually make it more vulnerable to errors during computation of large data, incoming data. The Davis Boulding is increased, and then a fast and smaller, but with that trade-off in accuracy. So one thing we realized was actually this prototype method was not going to be so effective on our project, just in case we were going to handle certain extremely large data input on certain days. So here we have the HDB scan model compression using uniform manifold approximation and projection alongside PCA. So as I had said earlier on, cleaning, standardization. Now PCA, which is principal component analysis, helps in noise reduction. It's going to get those 10 features and then reduce them again to 5 important ones, the most necessary in this case. Then UMAP, which is uniform manifold approximation and projection, is going to carry out learning using these 5 PCA components that we obtained, learns through them, and then brings out more number, like a larger number of clusters for better prediction. Yeah. This UMAP also works alongside the HDB scan clustering. So in this case, if let's say originally we had 3, we are going to have like 5 clusters. But 5 clusters on the very most important features from the original old 10 that we had obtained, we have now reduced to the most necessary, while also increasing the number of clusters, the number of types of the different clusters. So, right, for all that I've said about this project is HDB scan is one model that we successfully deployed as a production API. Then the system produces interpretable near real-time recommendations, which is actually a good thing to help the vendors using this system, help them interact more, help them understand, and also in the long run reduce food wastage. Then there is noise detection. Yeah, then limitations that we saw within this project were use of synthesized data, because most of the vendors actually don't keep records of their sales. So we actually had to move ahead and create our own data. That was one limitation. Then HDB scan approximate prediction does not guarantee cluster membership for every input. That's also another limitation of this system. And these are our next steps that we hope to implement. Thank you so much. This is still Group 17, Gloria Rugambwa. See you next time.